And today, what's interesting is I feel like before I'm excited to be at this lecture, but it's definitely something that it's been a while since we've been working on inverse problems. I recently got pulled back into the inverse problem because of this deep learning stuff. I want to talk a little bit about how these are connected to things I used to do. I also figured, based on the morning session, that I should change the title to P. Stan. So now, I figured now we're really appropriate for where we're at today. All right, so this talk is based on a collaboration with Anju Kanazawa, who is a brilliant new faculty at Berkeley. She's not even new anymore. She's been there for a few years. But it's been a big influence on the way I think about the role of neural nets in signal processing problems. And Anju also made most of these slides. I've modified them to be, to my own predilections. So if they look beautiful, that's because of Anju, and if they're offensive, that's because of me. Matt Tanchik and Bennett Mildenhall also made several of these slides for a tutorial that they gave with Anju not too long ago. Matt was a co-author on one of the papers I'll be talking about, which was led by Sarah Friedrich-Kyle, who is one of my graduate students who is graduating this year, and Alex Ju was the other student lead on the project I'll talk about. So before I talk about our project together, let me just have some philosophical musings about inverse problems. So I think that, microscopy and computational microscopy is probably I think the core of what I think about when I think of a quintessential inverse problem, right? So inverse problems always have trying to reconstruct a latent state from observations. And those observations usually have some associated forward model that we can leverage. So we usually know how to go from, or at least have a model in our head of how we go from physical reality to whatever comes out the other side of our microscope. And then the question is, whatever data stream we've got there, how do we now turn that back into some representation of physical reality? Now, of course, the problem with this inverse map is one, even if it's really easy to simulate F forward, simulating rho backwards, not ever cut and dry. And moreover, it's almost never invertible, right? This is the big problem we have. We have some slice. There are lots of things that could have given us that slice. And so we have to use something else that we know to recreate what we think was behind the scenes. And what I love is that we have, I've only been at this workshop for a couple of days, and it comes up multiple times, how we know that we actually got the right answer when we do the inverse problem still is one of the more interesting questions that we could talk about over beers. But a lot of times we sweep that under the rug a bit if it looks good enough. Now, when I was thinking about deep learning and inverse problems before, first my history is solving inverse problems using optimization. If you could set up that X has to live in some, that the actual X you care about lives in some subset of this possible models, you could just minimize a loss function using your forward dynamics. And there are a variety of different ways you could do that. I'll talk about that in a second. The machine learning approach, and actually what we have been actually saw in the previous talk, the machine learning approach was that you can estimate the inverse map from examples. So if I have this forward model that I could easily generate, I could generate a huge chunk of Y's and X pairs and figure out just how to fit the way back from Y to X. Okay, and that's another approach. But what I'm going to talk about today is this other thing that people have been doing that's weirding me out and trying to make sense of. So I'm not going to talk about machine learning from examples, even though I actually think this is a great way to solve inverse problems. If I have a simulator I really trust, and I can generate millions and millions of images, and I have, as you said, an IT person who's willing to train it, that's probably going to be a pretty good way to solve a lot of inverse problems. But there's something else that people have been doing, which I'm trying to wrap my head around. So let's go back to this optimization formulation, not the machine learning formulation. So one of the big questions is, that the set of x's, if I use every possible x, I'm going to have lots of possible fits to the data. So you have to somehow constrain x to take this underdetermined problem and make it overdetermined. And one of the classical things, which is, there it is again, Stan. Some people call it compressive sensing, but a lot of times you just call it sparse recovery, or maybe we call it L1 associated minimization problems, say that you model the latent signal as sparse in some basis. You could also model the latent signal as sparse in some nonlinear basis, and this was something that myself and my collaborators did for many years, and so you could have low-rank matrices or other structured operators under the hood. And you could also use an image prior as your underlying basis. I couldn't come to IPAM and not talk about TV. I think it's required for every talk you add it once. Actually, I'm going to add it again, Stan. It's coming back. Stan said he'd give me $5 for every TV reference, so keep track. Now, another thing, I think Reinhard was going to talk about this tomorrow, right? Yes, or maybe you've seen this, is having what's called a deep image prior. And these are also very interesting and powerful. And here the idea is that you want X to be the output of some neural network. So the X's that you're going to allow be the output of some neural network that is somehow reasonable under image statistics. So there are lots of different models, and again, I don't want to talk too much about this right now, lots of different models where you could say there are generative ways to make images, and you would say that the true X should be generated by one of these neural generators. Okay, so that's another possibility. But then there's this last one, and this is the one I don't get, which I call deep nihilism, because it's just throwing neural nets at every problem. And that's just saying that X is just going to be, the output of a neural net with no priors whatsoever, no plausibility, just be the neural net will give us the output. X is the map from something to something, and the neural net will be the output. And so the thing that's funny about what I call deep nihilism is, why people like it is because you could always do it. I could always put a neural net in as a function approximation of something. Always allowed to. It's always going to type check. It's easy to do. It's very easy to just code up in PyTorch or whatever folks are using right now and hit go. But there are problems with this approach. I'm going to talk about one particular example and kind of highlight what the problems are, is that it's very easy to do, but you're always going to be pretty slow. You're going to be computationally inefficient. It's going to be hard to understand what the heck you just did and why it worked, if it worked. And then if you actually care about using this in the context of not necessarily just making a pretty image, but using that pretty image to make the decision about either the decision about someone's healthcare treatment or the decision about whether or not my printing device is actually working at a microscale. Okay, now these things actually have important consequences. So it'd be good to know whether or not, to have some way of understanding how robust these deep solutions are to data perturbations. And so the question that I always ask, and I've asked this all over the place, this has been something I've been doing for about 5 years, is anytime someone's using neural nets, I'm like, do we need the neural net? And so today I'm going to walk through an example where spoiler alert, no. I'm going to walk through the example where the answer is no. And I want to talk about how we got to that solution without the neural network, and at the very end come back and saying, well, maybe there are still things that are lacking about the non-neural solutions, which is why people are choosing other things. In some sense, what I want to talk about in this talk is, I spent a good chunk of my life, Mike was there, how long did we spend doing optimization-driven signal processing, and no one does optimization-driven signal processing anymore. So I feel like it was like we failed in many regards. And I would like to understand a little bit more about, at least temporarily, what failed and how could we get people excited about optimization-driven signal processing again.
Quick question.
Yeah.
What was the difference between the deep nihilism and the image of a generative network? Are you saying throw away the fact that there is a forward model at all and just learn a neural network that...
Yes. We're just and to some extent, I'm going to be much more specific in a second, and you'll see what... I'm going to go through a very specific example. Do I have it here? Yes. I'm going to go through this very particular example, and I think it'll become a little bit clearer. And also, again, I'd love to have more questions. So throw them at me as they go. The thing I like about this example is there's actually beautiful math that happens in the middle before we throw the neural net in. And I thought it was interesting, so I figured I'd share it with you folks as well. And the problem that we ended up looking at, and this has been all the rage at UC Berkeley for the past few years and in the computer vision community, is this problem of novel view synthesis. And the idea of novel view synthesis is I have images, photographs of an object. But these, as you can see with this object here, I'm taking the photograph from different angles. And what I'd like to do is stitch these together and get a multidimensional rendering of the object. Okay, so this is called a novel view synthesis, to be able to, from a few images, construct perhaps a whole 3D volume rendering of the object. Okay, which has a feel of like a nice classical inverse problem to it. So the solution that has been incredibly popular, despite only being a couple years old, has been what's called the Neural Radiance field. And I'm going to describe today how the Neural Radiance field works. Here is just an example of two pictures that we're stitching around here. Each of these scenes was taken by taking a bunch of pictures, running something with a neural net in the middle, and then outputting a 3D model. And I'm going to talk about actually how they did it and what went into it. And then the question is, you know, which part of this is actually needed to be able to go from 2D images to 3D reconstructions? The thing that's been crazy, like I said, there are so many Nerf papers now. It's clearly captured some part of the mindset of the computer vision community. Like there are, and I'm not going to try to go into the psychology of why there are 10 Nerf papers every day on the archive, but let's at least say that there are 10 Nerf papers every day on the archive doing something or the other.
Nerf is not supposed to reconstruct the right answer. It's supposed to reconstruct something that looks good, right?
But Stan, how is that different from every other imaging thing we do?
Oh, TV gets the right answer, of course.
Ah, oh, there we go. Let's see. All right, let me describe, like, there are two things that go into making the Nerf, but I want to kind of walk you through the main idea. Because also, I think it's really, the forward model is really lovely. It's, in a way, a lot simpler than a lot of graphics models, and I feel like that is part of what captures the imagination and why everybody's so excited about it, is it's kind of an alternative to, it's a way to generate a rendering algorithm that you can differentiate. And once I could differentiate, I could put neural networks in the middle, and then I could do whatever I want. But also, if I have something that's differentiable, I think it should be open to a variety of different things. So when I want to render a scene, I have to think about all of the different ways light can get from the camera to different parts of the scene. And obviously, we have this kind of reciprocity that actually means, it tells me how light gets from the scene to the camera as well. So if I take this ray, what I could do in surface rendering is I can know a model of the surfaces in the scene, and then I can query all these different points on the surface and see wherever, did the ray hit close to those points, and then generate the ray, a contact based on that. That's called a surface rendering. Volume rendering, there's a hit. Okay, volume rendering, on the other hand, loops over the points in the ray rather than looping over points in the scene. It just looks at the points in the ray, and then it says, did any of these hit the volume? Boom, there's my hit. So volume rendering, in some sense, well, it depends on what your primitive is, but if you are willing to shoot lots of rays, and that is computationally efficient for you, this actually poses a nice ray-centric solution. Okay, and the way that this then gets turned into an actual pixel value is the following. There's this volumetric formulation. So you model the scene as just a cloud of stuff. It's a cloud of stuff, and the question is, can the ray go from the camera out to space without hitting anything? Like, when is it going to actually hit something in the scene? So if the ray hits a particle, then you return the color. And so here's a particle, color goes back to the camera. So what's the probability, if I have this volume of stuff and I shoot out a ray at random, what's the probability of hitting something in the scene? So we assume that there is this density, sigma, and that sigma is going to define the probability of actually hitting, of the ray actually hitting something in the object. Okay, and so it's just, the probability of actually making a hit is just whatever that volume density is at this point times dt, which is my little infinitesimal distance along that ray. And the probability that there's no hits before this particular point on the ray, I'm going to define to be the transmittance function t. Okay, so that's the probability that I got all the way here and I didn't hit anything. That's t. Yes?
Is this with or without obstruction along the ray? So if there are particles behind each other?
Well, so here, that's a great question. So now you're asking, like, why, I can either have this object be like a diffuse cloud, or if it's a solid object, there would have been a hit with probability 1 here, right? So this allows for probability 1 events to happen, right? So there would be after this, there would be the probability of having a hit before t will be
So it is
1.
with obstruction of
Yes, but it just depends. But it also allows you to have objects which don't hit with probability 1, and those will be translucent or transparent for that matter. So it allows you to have a variety of different surface types, all within this model. Okay, so that's the transmittance function is just the probability that I didn't hit anything before I got to t. And from this, I can actually compute the transmittance function from the volume density. And there's just a simple calculation that we could do, which is that the probability that I hit at t is equal to the probability that I didn't hit it before t times the probability I do hit it at t. So that's t times this sigma dt. Simple. And then how do I compute sigma? Well, I had to say that the probability that there's no hit before t plus a differential, little dt, is t dt times 1 minus sigma of t dt. And this is a differential equation that I can solve. And it turns out that the solution is that the transmittance is just an integral, a very specific integral. It's the exponential of the integral of the density. Okay, and you guys could stand this exercise for Stan to work out. He says he loves logarithms. Well, here it would be. Anyway, so that is a very simple formula for the transmittance. And I can now combine that with now I wanted to say, what's the probability that actually the first hit happens here? Well, that's again the probability that I didn't hit before t, which I just computed, that's this transmittance function, times my infinitesimal volume element there. So it's just this transmittance function times sigma of t. Now this closes my derivation. So the expected color that we get is this formula. This was the lead up to this formula. So now I can integrate along any ray. What I do is I take my volume density, I take the associated color at each of those places, multiply them together, multiply them by this transmittance function, which is an integral of all of these, of the volume density, and I compute that full integral together along the ray, and that gives me the color I should return. Okay, so what are the takeaways here? Well, this whole thing is just a nice differentiable object. I am just computing a line integral, and if I didn't know sigma or c, and I wanted to find them, well, now I have something I can differentiate, which is very nice. And very different, if people have ever seen how you would do surface rendering uses probabilistic ray tracing, much harder to figure out how to perturb and take derivatives of. People have been working on differentiable rendering for a long time. It can be done, but it doesn't have this these things can just be fed into PyTorch, which is what people get excited about. And in particular, if you now look at how they solve the multiview synthesis problem, it's just going to use that formula. So the multiview synthesis says, I want to minimize the sum over all of the rays I've seen. Omega is going to be the set of seen rays, because you don't see everything. You see a few views, but you know where the camera is, so I can tell you what those rays that I've seen are. And I'm just going to minimize least squares loss. Simple enough. Pixel loss. Now I know that my model should be this integral, which I have now simply written out by finite differencing. And the finite differencing formula is really nice. It's just the difference of the two transmittances next to each other. The transmittance still is the same thing. And the deltas here are given by however you're discretizing. And then Ci is the associated color. Now what is Ci and sigma I? Ci are the values of the color along the ray at that ray point and the view direction. And then the sigma is the value of the density along the ray. Okay, so everything is nice and out here for me. I can get this spinning thing if I could solve this inverse problem. Everything is differentiable. If I wanted to, I could just, there are two things that are also very interesting, is that if I know sigma, this whole thing is linear in C. It's a linear inverse problem in C if I know sigma, because C is only entering here. So it's a beautiful linear inverse problem if I know sigma. It's actually only mildly nonlinear in sigma if the C is constant. And what I mean by that is let's say C is always a constant, this is a telescoping sum. So I'm only left with the full transmittance. In some sense, when C is constant, it reduces back to CT. it is equivalent to computed tomography when the color is constant. But when I have varying color, it's one step into nonlinearity land. And that's what makes it a bit of a challenge. And so I could either try to do some nonlinear optimization, where I optimize over like a full voxel, right? This is a 5-dimensional thing. So I have a 5-dimensional thing that I could just voxelize in 5D. But as we know, 5D is definitely where the curse of dimensionality is kicking us. Or I could just say that C and sigma are neural networks. Meaning you take x, y, z, theta, phi, feed that into a neural network, and then output 3 color channels and one volume density channel. Maps 5 dimensions to 4 dimensions. And again, this is where I'm like, why is it a neural network? What kind of neural network? Well, how about a 12-layer fully connected neural network with some residual connections? That's what it's going to be. Why? Because I can code it. And that we call Nerf. And actually, you have to do a few other things. You have to do a couple other bells and whistles, and it's in the paper. You can read it. The fact that they did it is beautiful, but the decisions that they make, you're never clear why any of these things are there. And the question is then, I find this confusing, but it works. Nobody ever did this one. Which is better? Well, we decided let's try this one. What happens if we just make voxels? Where do we run into issues? Do we run out of memory? Do we run into all these other issues? Let's see how we could do it. Do we need these neural nets there? So again, the neural radiance fields in the slide is, I have all these different input images of an object. I build a neural net that takes x, y, z, and my view directions, literally feeds it through some fully connected mumbo jumbo, outputs RGB and sigma. And I use this volumetric rendering function to build my optimization problem. I send it through the Atom solver or whatever solver people are using today, and I get out really beautiful pictures. Now the problem and the practical challenges with Nerf is that this is slow. Right? You're taking hundreds of pictures, you're feeding it through PyTorch, you have a very unstructured neural network. It does really take a long time. And what I'm going to and even after the fact, once you start to try to render it back, it's still very slow. It takes 30 seconds to generate, without any kind of optimization, just running through PyTorch, generating new views takes 30 seconds per frame. So neither of these are particularly appealing, even if the images are beautiful. Oh, that's the wrong button. That's the right button. So what's our different approach? The different approach is something that we've called Planoxyls, because Angju is really, that's a giant fan of the planoptic function. So this is like the idea. The planoptic function, more or less, is roughly this color thing. It's the idea that if I can model in space the color associated with a particular view direction and my position, I can model anything. And this is something developed by Adelson in the 80s. What our main approach is we have a grid. So like I said, gridding in 5 dimensions is horrible. But these theta and phi are a view direction. They live on the sphere. So what I could do is instead of that say, well, what I could have is just a spherical harmonics basis. We know that for most rendering, I don't need very high dimensional spherical harmonics to represent very realistic images from a fixed point on a sphere. This has actually been pretty standard for a long time. So I could just take like the first 2 degrees of spherical harmonics, but then at every position in space have a spatially varying spherical harmonic coefficient. What this means is that I have to store, let's say, 27 coefficients at every point in 3D space. But that's considerably less than making a 5-dimensional volume. So it's a 3-dimensional volume where at each point in the volume I'm storing 20 or 30 coefficients. Okay, and that's the planoptic volume element. So now we've solved at least the memory problem, and we can just run an optimization solver. And I'm going to be honest, I wanted us to try something very sophisticated because I love optimization algorithms, but we ran just gradient descent. It's fine. It's fine. Gradient descent's a great algorithm. And so let's see. This animation, which was made by Matt Tanchik and is just gorgeous, kind of sums up the whole thing. You cast the ray. The ray goes through the volume. It hits these voxels, which are very easy to find and check and look up. At each of these points, in the corners, we have spherical harmonics. And then each of these spherical harmonics can be interpolated. We just use trilinear interpolation. And then once you get the trilinear interpolation, you get your point on the ficus there. And you do this from all the different rays that you've captured, and you generate this beautiful plant. Look at that plant. And so, if I go forward, again, you have the sparse voxel grid that we maintain as we go through the different views. You store spherical harmonics at each point of or spherical harmonic coefficients at the corners, and then I can just trilinearly interpolate whenever a ray hits the box, and then use our volumetric rendering function plus maybe a little regularization. I'll talk about that at the end. Which regularization might we use? Just a little Osher special in there, and that to make the image look more crisp and realistic.
I was going to ask about that. I read a little bit about this stuff, and they're talking about difficulty with getting high frequencies.
Yeah.
And they do something special. And you regularize.
We just regularize.
I approve.
Okay. That's all we do. And I'm going to show you a picture of that. Very much, so I'll come back to that. Before I do that, though, I always like to have our little bragging about speed. You know, a lot of times in optimization, you just want to run races. So on the left, we have Nerf. On the right, we have our Planoxyls model, which is already done. I don't know what's happening over there with the Nerf thing.
What's the time scale?
Seconds. I mean, it's what's sped up seconds. And that's where the image stops. Yes, go ahead.
Is there a difference between the resolution or the accuracy you can get of an extended object, the front and the back, or is that homogeneous?
Oh, could we do different scales in the front and the back of the object? Yeah, we will. Well, I'll show you that when we do.
If you have rays angling out on the sampling, I mean, you may not necessarily have that, but if you have that, then the sampling in the back will be worse than in the front, right? So
yes, and we do adapt that when we get to real scenes. So with this synthetic scene here, it doesn't matter because like it's a white background and nothing's happening. But as soon as you get to real scenes, yes, we have to adapt the way that we sample in order to make it to make sure you don't have exactly the problem you just pointed out. Yeah, right.
So what you optimize over are the alpha eyes and then these Y eyes.
The Y eyes are fixed. Sorry, just to be clear, I tried to write it out to be clear. But maybe it wasn't clear. YI just means spherical harmonic basis I. I guess I should have put the two coefficients there, right? Like then it would be clear. These are just the vanilla spherical harmonics. And we use, I think, up to degree 2. So it's like 28 coefficients, right? And so these alphas are changing. The alphas are what we search over. The Ys are just, the whatever they are. The standard trig formulas you get for spherical harmonics.
So what is the general dimensionality of this for the x, y, z voxels and then 27 basis functions for beta and phi? So what are the...
It's a lot of stuff to put together, right?
Yeah.
I was going to get to that at the end, but maybe I get to that now. I'm happy to jump around here. No, I think it's a great question. So here, the biggest downside, I mean, again, like that was really fast, right? It was like way faster than the neural nets. But again, the downside, I was going to save the downside for the end, but I'll tell you the downside now. The downside is voxels are still memory hogs. Because if you take 100 images, which is what we typically take for these scenes, they're usually about 100 images, and they're a resolution 800 by 800, and you have RGB, then the amount of data you actually have already is pretty big. It's 200 million pixels. The model that we're using is your spatial resolution cubed times the spherical harmonic coefficients, the number you're using, times 3. That's why I'm saying 20. I was trying to remember why it was 28, because it's 9 for the first 2 degrees of spherical harmonics, times 3, which is 27 plus 1. It's 28. I knew that number was in my head, and I couldn't remember why. There it is. But this also tells you now what the issue is, right? So if I have 128 cubed, that's a pretty low resolution. It's already 58 megabytes. And as I go up to 512, we're at like 3.7 gigabytes. And this is pretty big. And one of the nice things about Nerf, also I had to point out, it's 3.7 gigabytes without using sparsity. But another one of the big issues with, and something we had to tackle that was really difficult, or sorry, when I say we, this is definitely something that Alex and Sarah tackled, was we needed to have a good sparse representation. And this is something that it was really frustrating to me to go back to 2011 and look at all these papers we were writing about compressed sensing where we just never dealt with this. Or L1, where we never dealt with the fact that we always were just storing, effectively, full vectors, full matrices with lots of zeros in them. There was not a lot of thought or a lot of engineering behind having really fast, sparse representations. which is something I feel like is an oversight that we should have, if I can go back in my time machine, something I think we should have addressed. But the other thing to point out is like these neural radiance field models are like 8-layer, they are 8-layer fully connected networks with 256 activations. Why, I don't know. But that's what they are, and that's less than a meg. So since we can get similar quality to these neural radiance fields, we're definitely leaving something on the table. Like a factor of 4,000 in memory, right? And how we can actually, that's the big, it's a great question. Does that answer the question you're after? Yeah, that's the biggest limitation. It's also kind of amazing though, I mean, I think this also makes sense. Working on such a compressed model is why it's slow. Working in that compressed space is gonna be slow, as opposed to working in the uncompressed space. And we're better than this. I think we get this down to by a factor of 10 because of sparsity, but by the data structures that they built. But I think it's not 4,000. And figuring out how to get 4,000 would be really great. I can't remember what slide I was on.
Question.
Yeah, go, please.
So is there any other structure that you can exploit in the alphas? You mentioned sparsity, but is there any sort of like low rankness or anything like that you can exploit?
Well, there's going to be, I'm going to talk about this total variation in a second. So they definitely have that. So they definitely have low total variation. I was going to talk about that. Let me do that now. Uh-oh. My beach ball. Come on. There we go. This is the end result. So sorry, I forgot to show, like we do get about the same answer, like in terms of, this is PSNR, which do what you will with PSNR. It's a metric. We could have given you SSM2, I don't care. And the neural model takes 2 days to train. Maybe you can optimize that a bit, but we got it down to under 10 minutes. So we're also able to train these kind of like actual forward-facing real scenes using the same model. And again, though, here's where you actually have to do some special sampling to distinguish between foreground and background. Not just special sampling, we actually kind of like map the background onto, yeah. So the results show that the key component of the excitement behind this neural rendering is this beautiful volume renderer that's nice and differentiable. It really does capture everything, but the neural net allows us to add more compression. Okay, so I think that's probably the big take home is that slide. But I also have, let's see, what time is it? I have more pictures. And I also I was like, when do I get to talk about TV? Next slide, not this one, Sam, next slide. So there were a couple of things that we did that I think were pretty useful is a model that Alex had built, it's called Planoxyls, was just when it was pushing the rays through the volume, it was just doing nearest neighbor, looking at the nearest intersection to get the actual color value. It actually did make a lot of sense to use trilinear interpolation in these models. And it was fairly straightforward and easy to do, and you just get much better resolution of the objects to kind of get rid of a lot of different blur using this trilinear rather than the other kinds of interpolations. And certainly you could see why we need the 512. I mean, this is already the difference between 128 and 256 is already really big to get out sharp corners in the Lego. So that's this little light up in the top of the Lego. And then TV regularization was also really critical to make this work. So let me look at this again, because I always find this really counterintuitive. Which one needs, so it's clear that there's a difference between actually using TV and not using TV. We needed that to, now, the thing that's weird about Planoxyls, as Stan was mentioning, the neural radiance field approach had a hard time capturing high frequencies, and they had to do this funky thing to actually hard code those back in. The problem with using a pixel grid and no regularization is we just get high frequencies and all sorts of noise, and the total variation definitely helps to remove a lot of that. And there are these two in the middle that I'm looking at that I can't actually now remember which one actually matters more. It seems like you needed more structure in the spherical harmonics, though. Like, you can see these edges here where the spherical harmonics are capturing these weird shadows that shouldn't be there that go away when you use TV. So that's just to answer your question, you got me. But I also find, and this is one of these weird things of working in computer vision rather than microscopy, like these are computer vision papers. In computer vision papers, people just care about what looks good, not what it is. Especially Angju, to be clear, also to Angju cares about graphics. And like if you care about like the graphics end of computer vision, really all that does matter is if it looks good. For most of the things that we care about. To make an immersive environment, we just want it to look good. Any other questions about the TV stand? You're happy?
I'm thrilled.
You thrilled? Look at that, sounds thrilled. All right, so I have a lot of time, so I could do, I could show us lots of videos. Yeah, they are pretty cool. I love these models that they generated. They're like, so these are all these synthetic scenes that we can reconstruct, and they're all really neat in their own way. I think the other thing that I found really interesting is if you compare it to the ground truth. Let's see, there we go. Come on, show me the, oh no, we're just gonna go through more scenes. As you watch and you compare it to the ground truth, the neural model and the pixel model, or the voxel model, have different artifacts, which I think is funny. Like they don't perfectly recover. Here we know what the ground truth is, and they're definitely recovering slightly different versions of the ground truth. Like you could see like the speckle on this one versus the speckle on this one. They just look different. And I don't really know, I don't know why. This is always the weird thing. We never know why, and we play with our regularizers until it looks the way we want them to. But they're definitely capturing different parts of these synthetic models. Okay, so here is a real image. This is at the Natural History Museum on the Berkeley campus. I don't know where this flower is. They're both very pretty, but these are both captured with an actual camera and reconstructed using our different models. Here's like a few more real scenes of conference rooms. Everything kind of just looks like swirling cameras around this way because everybody ends up making the same demos. Let's see what else we got here at the end. I mean, they're kind of wild. They look really beautiful. Oh, more stuff. And I think that's it. Maybe not. Oh no, there's more. There's so much more. Anyway, whatever. We can go on all day. We can go on all day. And here's actually a 360-degree view, which was done by capturing an actual object on a table in 360.
Do you know roughly how many images are taken to
About 100. Yeah. This is wild. I love this foreground versus background. The reason why we can do that is that's just an artifact of how we actually did the ray tracing. So it's kind of cute that we can do that, but it's almost an artifact of the reconstruction rather than the actual reconstruction. Here, let's pause this for a second. Let me just say just quickly about that. Why could you do foreground and background? It's because you segment out the foreground and you render that in one coordinate system, and then you do an 1/r system for the background. And so that was just showing the difference between the 1/r versus the normal rendering. Let's see, let's play this guy. Oh, where are my tanks and temples? All right, it's not gonna work. Anyway, we'll go over here, takeaways. So I made takeaways. So I think at this point we can agree that the neural network, even though, this is the thing, you put neural in the title, helps to get the paper published, didn't really have anything to do with why the radiance fields were so powerful. This volume rendering is the key ingredient. The volume rendering itself, like it's a beautiful formula that you get out, that actually gives you a way to go from density to rendered images, and you can actually infer that density from a small number of 2D images, which is just amazing. And these explicit representations of voxels did lead to a considerably faster optimization. One second. There we go. So here's the question. Does this mean we throw out the neural networks? So not exactly. Now I have to say, Dominic was calling me on this, and he's right. I think I spent a lot of time telling people you don't necessarily have to use neural networks. I spend a lot of time on a lot of things like that, saying maybe you don't have to do this, there's an easier way. And I'm used to people not listening, and that's fine. If you choose to use this information as you want to use this information, I think that's fine. But I do think that the biggest issue that we have, and I think the one thing that really holds this back from being, well, there's two things that hold it back from being widely adopted. It's these two things. One, that voxel representation is still too large. And it's just, it limits even what the students can play around with, because you run out of GPU memory. I mean, so many architecture decisions in neural networks are made on what is the memory size on my GPU. So many of the architectural decisions are, I make it as big as the GPU will hold, and that's my architecture. And then in the paper, I write a bunch of other reasons. But the actual reason was, that's what the GPU would hold today. And that ends up being my model. So these voxel representations are a little bit too big, and they really do limit the amount of fast, rapid prototyping that we all can do. And the other thing is, like, in order to build this system, we wrote custom CUDA. Sorry, again, let's be really clear. Alex wrote custom CUDA implementation kernels to do a lot of the rendering operations, and that made it fast. And those things are exposed to all of us, but nobody really wants to do that. Everybody would much rather write something in Python. And if you have to wait a day, okay, so be it, right? So I think that we're fighting against two trends there. One is GPU memory is not infinite, and two, sometimes convenience gets in the way of efficiency. I think the other thing that's kind of fascinating, and Angju makes this point all the time, I just want to make this point as well, like, these ideas are not really new. Like, the rendering formulas that we were using for volume rendering are from the early 90s, and they were adapted. There were already crazy, amazing volume renderers in the 80s, and they just got simplified to their current state in the 90s. And there were all these ideas of doing analysis by synthesis, which is what the computer vision call, essentially, this kind of optimization approach to inverse problems. People 20 years ago were already trying things like this. So it is interesting that these ideas keep coming back. This is another thing I've noticed. The reason why that happens is because Moore's law is an amazing thing. I think that's just it. You get bored, you hit up against the limits in 2000, you go and work on something else, you come back 20 years later, and all of a sudden these things you were doing 20 years ago are so much better. And that's part of it, but it's also worth at least pointing out that we are kind of circling on a lot of ideas that are not very new, but maybe they are timely. And again, I'll come back to this. To me, the biggest open question, and I think this is an open question that affects everybody here, because it really limits the sorts of images we can create, especially once we want to move into multidimensional dynamic images. Certainly in the case if you want to do like dynamic MRI, if you want, I'm not sure what we can do in I could come up with other examples, but I think you all know what I mean, right? Like, if you want to do these things that are in 4 or 5 dimensions, we run into these memory limits very quickly. And why we don't have better data structures that are easily accessible, that people can solve these optimization problems with, I don't know. But it'd be cool to, I think it's a great thing to think about. So I think what's currently happening in the computer vision community is, people have been trying to work with better compressed representations. There's this, I actually find kind of wild thing that breaks these volumes down into rank 1 tensors. So they rebuild the volume as a sum of rank 1 tensors. I don't know why that's a reasonable model for a volume, but it seems to work. So sometimes the proof is the devil's in the details there. I would love to actually understand a little bit better about what is that the right compressed model for these volumes? Is there a better one? What else could we do? And also, I just really want to point out, this is one of these areas that's so hot. There is like 10 papers a day on arXiv that it's hard to keep up. So this is really only about half a year ago. I think there's plenty of stuff still to be figured out. Definitely in the computer vision community, what people are doing is just making the neural nets shallower, like 2 layers instead of 8. I guess that's 8th solution. Again, I get uncomfortable when we're just tuning the neural net to, we're picking the neural net based on computational convenience rather than based on any other reason. I'm getting uncomfortable. And yeah, I think that the big challenge to us old school optimizers out there, which I know there are several of us in the crowd, is like, I think one of the things Stephen Boyd was really big at hammering, and what was great about, I don't even remember what it was, CVX. Oh man, now I couldn't even remember what CVX is anymore. That's how far we are into the neural net revolution. But what was great about CVX, it was something that everybody could play with, and you would hit limits, but I think that was kind of part of, I actually think that's part of Stephen's design. He wanted a disciplined way to build optimization tools. But that tooling, unfortunately, it was hard to get a lot of buy-in to do more. Considering the amount of attention that's been given to supporting PyTorch. Now, Facebook throws money at that. Compare that to the amount of attention that's been given to supporting CVXPy, which is considerably less. I think that's sometimes we're dealing with capital forces beyond our academic controls. But it would be cool. I mean, I still think that this to me feels like one of these, if we build it, people will come. I think it's still something that we can aspire to. All right, anyway, I'm going to stop there with a blank screen. Appreciate you all listening. Happy to take other questions, show you more movies, talk about TV one more time. Can't afford it. But anyway, thanks so much.